Everyone, today is fun maths. 2 plus 2 equals to 5. Oh, what's this again? Today we are talking about inertia. What is inertia?
Hi everyone, today we'll be talking about Kirchhoff's law or Kirchhoff rule. Now, what do we use Kirchhoff law for? Kirchhoff law is used to analyze complex circuits that cannot be analyzed by Ohm's law. Now, when we have a very complex circuit that Ohm's law cannot analyze, you know that Ohm's law is follows this equation V equals to IR. If that circuit cannot just be simplified by this equation, so we say that we seek Kirchhoff's law or Kirchhoff's rule to talk about it. But what is actually a circuit? Now, a circuit is a closed loop. Assuming we have a closed loop like this, so that is a circuit that allows the electric current to flow through it. So it allows the electric current to flow through a closed loop. And mind you, a closed loop or a circuit is not always a rectangular form. It's just like taking two wires, connecting the two ends together. When you connect two ends together, you can use it to form any shapes. It can be an irregular shape. You can use it to form any shape of your choice, maybe rectangle, triangle, any irregular shapes. But to make it easy and well seen, that's why we use rectangular form, mostly rectangular form, to represent the circuit. Now, a circuit is a circuit is a closed loop that allows electric current to flow through them, and it must contain a power source. And a power source in this sense can be a battery. So this closed loop is not yet done. It must have a power source. It must have a power source. Now, not only that, it will have a power source, a conducting wire. This line like this that you are seeing is a conducting wire. It's not just a stagnant or a rigid thing. It's a wire, as I said earlier. And also it must have a load. Let me just put that load, like bulb. So in representing this bulb, we can use different things like resistor, capacitor, inductor to represent all those loads that we are talking about. So it must contain a cell and a load. Let me see, resistor being here, capacitor being here, and so on and so on, like that. So that is what we mean by a circuit. Now let's analyze what resistor and capacitor does and how to resolve them, because we need the fundamental knowledge of those two things in this Kirchhoff's law, mostly that resistor. For a resistor now, a resistor is an agent, or I can say it's a component that resists the flow of electric current. Now, and it is represented in two ways. It can be represented in this manner, or it is represented with a box like this. So it can be represented with a box like this, or like this squeezed wire. So what it does is just that it reduces the voltage across the circuit, because there are some voltage that is too high for each appliances. So to reduce the voltage, you step down the voltage from high voltage to like preferable voltage. We use resistor to do that. And we have two major things that we want to discuss about under this resistor. The first thing is how to add them, and we can see resistor combining together in series. It can be in series, and if it is in series, they go like this, something like this. It can even come like this, it can come like this, it can even go anywhere like that. Maybe wire comes out like this. Remember, I told you it's not a rigid, it is anything that you can stretch. Now this resistor is in series. This resistor like this is in series, and if you want to add them up, the total internal resistance will now become R1 plus R2. You add each value of the resistance together, and all the way to Rn. That's how we add in series. Let me now give you a clear picture of it. Let me take this middle part away so that it won't look ambiguous. For parallel connection now, it is in this manner. So if you have a resistor connected like this, we see that they are in parallel, and the total resistance is 1 over RT equals to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot 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 till Rn. This is the total resistance in it. But to now know if it is connected in series or it is connected in parallel, because there are some complex one that is, even if it is parallel, there is series in it. So how do you know? The only way you know is that first locate where the wire is coming from and where it is going out from. Now the wire is coming in from here and it's coming out from here. So if you should hold this place down, let me use another color. If you should hold this place down, because those are the two junctions whereby the wire enters and the wire leaves. Now the one up, the summation of everything up is in series, the summation of everything down is in series, but the one up and the one down are in parallel to each other. Hope you understand. The summation of every resistance that is on this long wire, because it's just only one wire that connects everything, that is in series, and for under also that is in series. So the summation of the one up and the one down, connection between these two and things are parallel connection. Hope you understand. For instance, if you have a resistance like this, so it goes like this, it goes like this, so it goes like this. Okay, so it's enter here and it's enter through, it goes out from here. Now to now know which one is in parallel, which one is series, first hold on to the places where the wire come out from and where the wire enters. Wire enters from here, it comes out from here, or it enters from here, it comes out from here, any place. Just hold on to the two junctions. Now from this junction all the way to this first junction that you head on to, they are all in series. So you add them linearly. Say this one is 2, this one is 3, this one is 4, this one is 2, this one is 3, this one is 4, assuming that is what the resistance is. So for series now, you just add all this together. 2 plus 3 plus 4, that is just 9. So the total resistance across this place is just 9. Now coming under also, you go all the way from here, you trace the wire, you go all the way from here to this place. All of them also are in series. If you should add them together, that is also 9. And then you can see that this one and this one are now in parallel to each other. So you can now use this the parallel reading, which is 1 over R total is equals to 1 over 9 plus 1 over 9, because those are the two resistance that we have. And by the time you calculate it, you will see that your total resistance is 9 over 2, which is 4.5. If you want to know more about this, you can let me know so that we can take many questions on this parallel and series connection. But our major focus today is on Kirchhoff's law. Hope you understand parallel and series connection. Let's move to capacitor. For capacitor now, capacitor is just a device that store electric energy. We are going to talk about capacitor in any separate video because it's much more than this video. Now, if you are now talking about capacitor also can be connected in series or in parallel. And don't forget, the notation for capacitor can either be this or it can be in this form. So if we now want to connect, if you connect capacitor in series, it's the same connection like this, but the calculation is quite different. So the calculation of this series in capacitor is just the reverse part of the resistor. Now for capacitor, if you want to calculate the total, the capacitance total is going to be 1 over capacitance total over 1 over C1 plus 1 over C2 plus all the way to 1 over Cn till the number of capacitor we have in series. That's how we calculate for capacitor. And for parallel connection, it's still the same way how we connect resistor. So it's the same way, and the calculation is just C1 plus C2 plus C3 plus all the way to Cn. Now let's now talk about the EMF, the voltage of a battery. Now it is important to know that the EMF of a battery is different from the terminal voltage of a battery. Now, for in a real sense, the EMF of a battery is not equal to the terminal voltage of the battery, but the EMF of a battery is equals to the terminal voltage of the battery if it is an ideal battery. An ideal battery has its internal resistance to be 0, but for EMF, for a real battery, doesn't have an internal resistance to be 0. It has a value. So the EMF of a battery and the potential, the difference across the terminal between the terminal are not the same. But that's not where we are going to. The symbol of EMF of a battery is like this. It wants to look like a capacitor. Capacitor has equal length, but this one does not have equal length. And mind you, the longer one tells you the positive side, and the shorter one tells you the negative side of the battery. Now, it can be connected in series also in this format. Okay, it can be connected in series also. We know that this is one cell, second cell, third cell, fourth cell, fifth cell, and sixth cell. So we have different cells like that. And these cells, you just add them together to give you the so the total voltage is now going to be E1 plus E2 plus E3 all the way to En. But there is something we need to know about this EMF of a thing. If it is being connected like this, you can see that this is positive to negative, and this is negative. Instead of positive negative, positive negative, positive negative, positive negative, positive negative, this is positive negative, negative positive, negative positive, positive negative. What you just do is that it's not something that is hard. What you just do is that, okay, if this one is 2, this one is 3, this one is 4, and this one is 2 also, let's assume that is the assigned value for each of the cell. Now this one that is positive negative, you can give it plus 2. This one is in opposite direction, right? They reversed it, so you will subtract it from it. This one also is in opposite direction, you subtract it from it. This one is in redimension of what you are taking, that is plus 2 also. And by the time you calculate, you have minus 3, and you just say it is just 3 voltage, which means that it's just moving to this side, it's not moving to the opposite side. We talk about the movement later in this video. So if it is now connected in parallel, now if it is connected in parallel in this sense, now what's actually happened is that once it is connected in parallel like this, they give you the total. E total is also equals to E1 plus is also equals to E2, which is also equals to E3. That is what they do. So it is always equals to each other when connected in parallel. Now, if it is in a case that the voltage here is not the same thing with the voltage here, maybe the voltage here is 3 and the voltage here is 4, the total one will be the higher one, which is the 4. So it's just you're going to take only one voltage in all of them, and it's always go for the higher one. But mostly they give you equal voltage, so you have only just one, which is just if it is 3, you have only just 3 as your total EMF. So that's that. Now let's dive into what Kirchhoff's rule says. Okay, we have resistor, we have capacitor, we have voltage. Let me call it voltage in terms of battery, and we have something that flows also, which is current in a circuit. Now it is important to know that this resistor in series current is the same, but in parallel it is voltage that is the same. Now for capacitor in series, we won't talk about current in capacitor, we talk about charge. The charge is the same, and in parallel also voltage also is the same. There is an acronym that I made for this. Now I call it PVSIC. PVSIC. If you can remember your PVC, your polyvinyl chloride. If you can remember your PVC, the one they used to make your pipe or your ceiling. If you remember PVC, you should be remember to remember PVSIC. And what does it say? It says in parallel connection for both capacitor and resistor, voltage is the same. In parallel connection, voltage is the same for both resistor and capacitor. In series connection, for resistor, current is the same. For capacitor, charge is the same. That's just what it means. So don't forget these acronyms. PVSIC. Let's put it here. PVSIC. It's interesting in remembering this. Now let's move to Kirchhoff. Now Kirchhoff that we'll be talking about is just resistor, current, and voltage, which we know as Ohm's law here. Now Kirchhoff is also applies to capacitor, but using Kirchhoff for capacitor, it's going to be ambiguous because you'll be differentiating. It will later lead to differential calculus. So to avoid that, for now we talk about only voltage and only resistance in the circuit. That's only what we talk about. Only resistance in the circuit will not include capacitor. Now let's talk about when to use Kirchhoff's law, because although it's applicable to everything, but not every time you quickly use Kirchhoff's law because it's a long process. So now let's move to how do we know if we should use Kirchhoff's law when you see a circuit. Now when you see a circuit, you know there are some circuits that you will see that that can look like this. Okay, let's assume resistor is here and it goes like this. Resistor is also here. Because they have two loops does not mean you should quickly rush into using Kirchhoff's law, because these two guys you can resolve them and have only one resistor. So you can just do that. But when do we now use Kirchhoff's law? We use Kirchhoff's law. The first thing you should check for is if we have multiple voltage. That's the first thing you should check. If you have multiple voltage source, then go ahead and use Kirchhoff's law. So it means if you have a cell here and you still have another battery here like this, and maybe resistance is here, and you want to find the current that flows in this circuit, you must use Kirchhoff's law in this principle. It can be 2, it can be 3. You use Kirchhoff's law for it. The second one is if you have complex resistor network. If you have complex resistor network, what do you mean by that? Mostly, especially, there are some resistors that they are connected that will be confused. Is it in series? Is it in parallel? Should we take it in series and parallel, or should we just forget about it? That you don't even know which parts that you should take in it. Most especially Winston's bridge, is an example of complex resistor network. We use Kirchhoff's laws to solve that also. For instance, if you have something like this, if you say you want to just resolve this resistor because you have only just one voltage source and you want to just use only just one resistor, and you take this and you take this, then you know that you are solving this in series and you are solving this in series, then both of them in parallel. But what about this? Is it going to go to this guy or is it going to go to this guy? You don't know. So we have a complex resistor network here. Then you should use Kirchhoff's law in solving that. So if you are looking for total internal resistance in this one, what you just do, instead of solving it like this, like complex way, what you just do is that you first find the current that flows through the resistance, and your EMF will be given, your voltage here will be given. So you just use V equals to IR. So after you looking for the current that flows there into everything, and you just use V equals to IR to find your total internal resistance. That's how total resistance rather. That's how we find the resistance in this guy. Lastly, the third way in knowing maybe we should use Kirchhoff or not is when you have two loop circuits, two loop or multi-loop circuit. If you have multi-loop circuit also, you should know that you should use Kirchhoff. Now moving to Kirchhoff's law. Now Kirchhoff has only two laws. The first law is junction rule or junction law. It can be junction law or you call it junction rule. And what does it say? It says the algebraic sum of currents is equals to 0. That is what it actually talks about. The algebraic sum of current at a junction is always equals to 0. Or you can also look at it in this way, that the sum of current that enters the a junction is equals to the sum of current that comes out from the junction. So you can say sum of currents that enter is equals to the sum of currents that leave that junction. That is the first law. And don't forget that the first law or the junction rule is based on conservative of electric charge. It's based on conservative of electric charge. So what do you mean by a junction? Let's first talk about a junction. So let's assume we have a circuit like this. Now you are moving. Okay, let's extend it like this. Now you are moving like this. 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 If you get to this place, no, you'll be confused where to go. Maybe you should go to the right or to the left. Then you are at a junction, not at this place. If you are at this place, you are not at the junction, because if you are moving like this and you reach here, you can't say you are lost or you don't know where to pass. You just pass this wire like this and you go. But once you get to a point whereby you have two or more different ways again, then you can say that you are at a junction. So that one goes up and that one goes to the other side. So that is what we mean by a junction. It can be a T junction like this, or 3 parts like this, or 4 parts. It can be more than 3 parts. That's for a junction. Now let's talk about the second rule. The second rule is the voltage rule. So we call it loop rule. Now for loop rule, it says that the algebraic sum of voltage in a loop is equals to 0. Now this is a loop. So this loop, the algebraic sum of current in this loop is equals to 0. And mind you, if I will ask you how many loops does this one have, this one has 3 loops, 1, 2, and everything all together, those are 3 loops. And if I have something like this, and I say how many loop it has, some people can say 1, 2, 3, 4, 5. You are not wrong, but don't look at it that way, because it's actually more ambiguous. Because if I should start with that, I will start dividing this into many sections, taking two parts, and say we are having loop, because I will just take this part and this part, take this part and this part, and we have many loops. And so we don't say that. What we just do is that we count the number of loop closed circuits we have. We have 1 here, we have 2 here, we have 3 here, and we take everything general and we say that is the fourth loop that we have in this guy. Now the sum of currents in each loop must be equals to 0. Now they said algebraic sum, which means you must consider the sign. So that leads us to the steps in solving this. But before we move to the steps in solving Kirchhoff's law, the loop rule is its conservation of electric force or energy. So that is for the loop law. Now let's move to the steps in which we can solve Kirchhoff. Okay, for the steps in which we solve Kirchhoff's law, I just have only 4 of them. They are not hard at all. They are just 4. And once you know the 4, you have understood Kirchhoff like never before. Now, What are the four? The first one is that you find the direction, or you assign the direction of current. That is the first thing you do. Either you assign it or you find it, because they may have assigned it for you in the question. So you locate where the direction is facing, or you yourself, you are the one that will assign it to it yourself. Now we'll be talking about how to assign direction to current later. Now the second thing is you find the polarity of the resistor. Now the polarity of resistor, because resistor is a device that, or a component that doesn't have polarity, positive and negative. You use positive and negative, you can turn it other way around, it can be any place, so it doesn't have polarity. So when solving in this question, it is better you assign resistor polarity to the resistor. So that is the second law, the second step. The third step is now to use your junction law. We call it KJL, Kirchhoff's junction law. You can use your Kirchhoff junction law. And the third one is use your KVL, which is Kirchhoff voltage law. So that's what we are going down. Those are the four steps in this. Now let's see how we can use them one after the other. Now let me first take a simple circuit first to explain what the currents, the laws will look like. Now if you have something like this in this circuit and we want to assign the direction of the current, can either be assigned two ways. They can give you in this way, or they can say that it goes like this. They will give you the label of the current, because if you have a junction, therefore we should have more than one current, because current divides once it gets to junction. Now this is how current does when it gets to junction. Assuming we have a junction like this, so it is important to know that the current we are talking about, the conventional current, is just an assumption, because before electron was discovered, that was how they use it back then, that okay, this is how current should flow inside the circuit. And later then that electron was discovered, and they saw that electrons is the one that actually from negative to positive terminal, then current is just, and they did not change the law that current flow from positive to negative. It's just that they know that okay, current should flow in opposite direction, because we know that for every action there must be an equal and opposite reaction. That's what they just note there, that okay, let current flow this way. But conventional current is just an assumption. It's not a particle that moves or something that is real. The only thing that moves in the circuit is the electron. Current moves from positive terminal of the battery to the negative terminal of the battery, according to how I said. And we know that the number of electrons that leaves the negative terminal of the battery must be equal to the number of electrons that will enter the positive terminal of the battery. So current flow in opposite direction to electron. That's what we say. So we can now say that our current flows from positive terminal like this, it's moving like this, it's moving like this. Then when it gets to junction, it will divide. Some of it will move like this, some of it will move like this. So if some move like this, some move like this, they divide. Now if this is I1, this will be I2, this will be I3, because it has been divided into two parts. Now see, as I2 is moving, also is moving along this wire, it gets to this junction. I3 also is moving, it gets to this junction. As they got to this junction, they sum up again to I1, which is this I1, because the total current that leaves must be the total current that enters again. So they sum up again to this I1, then this should be I1. That's why if you are taking direction of current, or you are using KJL, you can take one of the two loops, you are still going to be correct. Just note where the current is moving. That's the direction of current that we are talking about. So the direction of current is from positive to negative, and note that and that very well. So when it gets to junction, it divides into two parts which move like this. And mind you, more current flows into a low resistance. Low current flows into high resistance voltage. So if low current flows into high resistance, and low current in high currents in low resistance, they later meet at the junction at the same time, and they move to the negative terminal of the battery. So that is how the direction of the current it works. And mind you, if you have more than two cells, say we have another cell like this, All right, inside this one we have 1 here, we have 1 here. If this is 4 and this is 7, now you may be thinking, no, this will leave, current will leave from this positive to this place, and current will leave here also to this place. But which direction of current, which current direction will you take for your current? Now, the one that has high voltage will tell you where it flows. So this one has high voltage. It's like saying you are pushing with 4 and this is pushing with 3. Then the director of the current should move like this, because this one have high voltage than this. And it doesn't mean if you take this also as your direction of current, you are not wrong. What will just happen is that when you finally solve your answer, you get your current to be negative something. So having negative something tells you that you are moving in opposite direction to that current itself. So it doesn't matter if you do not get the direction of current very well. So if you take it to the right and it ought to move to the left, you have no issue. It's just that your solution is going to have negative answers, and that tells you that the direction in which you took was ought to be in opposite direction. So we don't have current and the problem with direction of current. So we are done with the first part. Now let's move to the second part, which is polarity of resistor. Now the polarity of resistor depend on the direction of current. Note that the polarity of the resistor depend on the direction of the current. Now let's use the same example that we had there, which we have something like this. All right, from this first one. Now this is 7 voltage and this is 4 voltage, and assuming you are taking this direction now, it means current is leaving like this. So current will move like this and enter like this. And mind you, the polarity of voltage cannot change. It can never change. The positive terminal is always the positive terminal. It doesn't change. Now, as the positive current leaves, it enters the resistor from positive side and leaves the resistor from negative side. It enters from positive and leave at negative. Now it will enter here. Entering here is positive, coming out here is negative. Now coming in the other way around, also positive here, negative here, and current continues to flow like that. So current will flow like this in the terminal. If you are taking an opposite direction for your current, let's assume you have 4 years and you are having 7 here, and the direction you want to take is like this, it is opposite to the first direction. It's still the same thing. Just make sure you are sticking to what you are using. Okay, I'm taking in opposite direction. Remember, it moves from positive to negative, so my current is moving like this. Here will be positive like that, here will be negative. Remember, this one cannot be polarized, so here is positive, here is negative, and that is how it moves on this thing. So if you now solve the question finish, you will now see that one is negative, one is positive. That will now tell you the right position or the right way the current should flow. So that is that about the polarity of resistor. It is the current enters from positive of the resistor and leaves at the negative of it. Now let's move to the third one, KJL, the junction law. Now for the junction law, now you have something like this. And you know that this is a junction that we are to note. This is a junction that we have to note. So let's assume current is flowing like this and current is flowing like this, flowing like this. So if this is how current is flowing, now what happen is that the one that enters, which is I, or you can name it I1, but if it is being labeled for you, use the one labeled in the diagram. So if this is I, saying we are using I, this is my I, and this is my I1, and this is my I2, then I can say that my I1, my ordinary I, is the only one that is entering this junction. You can see is the one that is entering this junction. Other are leaving the junction. So I1 should be equal to I1. I must be equal to I1 plus I2. That's how we solve that. But assuming this I2 is facing up like this, so what you just do is that, okay, I1 is entering, I is entering rather, and I2 is entering. So you say I plus I2 is equals to I1, because this one enters, then the sum of them should leave the should leave at I1. That is just the KJL. It's not at all. That's just the KJL rule. And mind you, note that if this one is going, it is not possible for current to move like this, current to move like this, and current to move like this. Like this one is entering, this one is entering, this one is entering, and there is no leaving, there's no exit. It's not possible. That's what Kirchhoff is telling you. It is not possible. And it is not possible for current to leave, current should leave, and current should leave. Where is the source? Where is it coming from? It's not possible like that. In this case, like if you have a case whereby there is battery here, there is battery here, there is battery here, saying that this is positive terminal, but current should flow like this is positive terminal, current should flow like this is positive terminal, current should flow like this. What happened at this junction is that this one enters, this one enter, and this one enter, and that is wrong, because there's no how currents will flow. And then you must know that one must leave. So if you take this as leaving, then you know that the sum of this must leave here. So if you are getting a negative answer, it means you are to just reverse the way they enters the junction. That's just it. That's the only thing you should know about junction law. And mind you, if this is 7 and this is 9 and this is maybe 2, that's how they will move. This one will push its own, this one will push its own, and they move like this. Or this one push and share it to both of them, either of the two, depending on what you do. So that is that about that. Now let's move to voltage law. All right, now let's talk about KVL, the voltage law, the loop law. Now I'm using only just single loop to explain, and in my examples or the examples that we'll be solving, we'll be using more than one. Loop. Now we know that this is the positive terminal of the battery, then voltage should flow like this, voltage should flow like this, and since it's just only one loop, there is no junction, it's the same voltage that flows that goes all around, so it is just I1 that we move all around, so we don't need to label it I1, I2, I3. Now moving here like this, current is entering through this place, so here is positive, here is negative. Current is entering through this place, here is positive, here is negative. Current enters this place like that, and that is all. Remember, this is the positive of the battery and this is the negative. There is no polarity. Now if you want to use the loop law, the thing is to take your direction, the direction at which you want to walk. You can either walk in a clockwise way or you walk in anti-clockwise way. That is your own choice. It doesn't matter the way you go, just know the solving. Now here I'm going in anti-clockwise way. Now if I'm going in anti-clockwise way, how does this happen? Now you take them one after the other. Now if you are coming out from positive terminal of something, that means that your voltage should be positive. If you are coming out from the negative terminal of or negative part of that place, that means that your voltage should be negative. Now from this battery, now I'm going like this. Remember, I'm going anti-clockwise, so I'm moving like this. So moving like this means I'm coming out from the positive terminal. Then this should be okay. If I should call this one V, this should be plus V, because it is moving in positive terminal. Like I come out from the positive terminal, moving like this, and coming here, I'm entering from positive. Coming out from negative means this should be negative, because I'm entering from negative. So remember that our current is I, and we are comparing voltage, not resistor. So I will multiply IR, where V equals to IR. We know voltage equals to IR. So the current that enters this place is I1, which is I times R2. Do we understand? I times R2, but negative because we are coming out from negative part. Now here also we are coming out from negative part, so that is minus I times R1. Everything must be equals to 0, and then you solve this, and that is how junction KVL works. But if you want to take opposite direction, it's still the same thing. Let's assume we are going in anti-clockwise way. Let's assume we are moving in this direction. Now we are moving in opposite direction, which means we are moving like this, we are moving like this, we are moving like this. All right, then we know that this is from positive to negative. Then we have negative V, negative to positive, positive IR1, negative to positive, positive IR2 equals to 0 also. We can see if I should bring this one to the other side or transfer everything to the other side, you get the first equation part. Again, it's still the same thing. So that is how our junction voltage law works. Now let's move to examples.